Hello, it's Kevin here. I'm going to explain a proof, just for some reason. So here's is on my computer here. Let's say A is a set, and we denote A naught as its set of interior points. Now, who's watching this? Do you know what a set is? Do you know what an interior point is? Okay, a set is just a collection of unique elements. An interior point is a little more tricky. This is an element in the set, such that if I draw some epsilon ball around that element, the epsilon ball is still within the set, and that means all points within the epsilon ball are also within the set. Did you understand that? Maybe, maybe not. But anyways, let's go. We prove that this set of interior points is always open. What does it mean for a set to be open? It means that for all elements in the set, each element corresponds to an epsilon ball, such that the epsilon ball is a subset of the set itself. So we want to show that if A naught is open, all interior points have epsilon balls that are inside A naught. Now, we begin. Take an arbitrary x in A naught. So this is an arbitrary interior point. Now, as we know that it's an interior point of A, there exists an epsilon ball that's a subset of A. We want to show it's a subset for A naught as well. Now, we consider an arbitrary y inside this epsilon ball. Now this y, we know it's in the set A, but we don't know it's an interior point. If we know it's an interior point, then we'll be done, so we want to show it. Now, we take this y, take another ball around the y. Now, the way we define this ball is very important. We want this ball to be smaller than the epsilon ball of x, because a subset of a ball, which is a subset of A, means that that ball is a subset of A as well, which means that y would be an interior point. Now consider this. The distance between x and y in x's epsilon ball will always be less than the radius of the ball. Now, we define r, the radius of y's epsilon ball, as epsilon minus the distance between x and y. Now this means that the epsilon ball of y will always reside inside the epsilon ball of x. Don't believe me? Draw it out. The distance between x and y can be arbitrary. Epsilon is fixed, but the distance can change, right? If we take a ball very, very close to the edge of x's epsilon ball, we take a point, my apologies, we take a y point close to the edge, that means the distance between x and y is pretty big. It's almost epsilon. So we draw a ball around that y with just the distance, well, that's going to go outside the epsilon ball of x. So we take the radius as epsilon minus the distance, so we get that little buffer point. Draw it on a paper if you don't believe me. But let's use triangle inequality now. Let's take a z inside y's epsilon ball. Like before, we know the distance between y and z is less than the radius of y. Similarly, from before, right, the distance between x and y was less than the radius epsilon. So the distance between y and z is less than the radius of y. Then, we have the distance between x and z is less than or equal to the distance of y and z plus the distance between x and y. Again, if you don't believe me, draw it on a piece of paper. But we know that the distance between y and z is less than r. So the distance between y and z plus the distance between x and y is less than r plus the distance of x and y. But that equals the distance, r equals epsilon minus d of xy. So we have r plus d of xy equals epsilon minus d of xy plus d of xy, which equals epsilon. So we've shown that the distance between x and z is less than epsilon. Well, if you take some z and the distance to x is less than epsilon, that means z is an element of x's ball. But before we asserted that z was an element of y's ball, so that means y's ball must be an x's ball. But x's ball is inside A, so y's ball is inside x's ball, which is inside A, so y's ball is inside A. But guess what? This means that y is an interior point. This is the definition of an interior point. But here's the big thing. We've shown this for an arbitrary y. We picked a random y. That means for any random y we pick, it's inside the epsilon ball. Then y is an interior point. And if we go all the way back to the beginning, I picked a random x that's an interior point. But as it's random, it applies to all of them. So for every x that's an interior point, the epsilon ball of x is within the set of interior points. So for all x in the interior points, the ball is also a subset of the interior points. QED, we are done. Oh, recording audio through USB mic. Yeah, last time I did not have my earbuds in. Next proof. All right, you probably didn't understand the first one. I rewatched it. I got it because I just did it, but if you don't draw any of the pictures and you don't even have any text on the screen, of course you're not gonna know what's going on. But whatever. Next proof. Let's read off the problem on my computer here. Now, we have some random set. Okay, you know what a set is, I just explained it. We assert that the set is open, right? If you don't remember what open means, search it up on Google, ask ChatGPT, watch my last video. Now, the set is open, and it's also a subset of another set, A. Now, we want to assert, we want to prove that as B is open and B is a subset of A, then B is also a subset of A's interior points. Proof. Consider that B is open. So for all elements in B, there exists an epsilon ball such that the epsilon ball is a subset of B itself. But as B is a subset of A, that epsilon ball is also a subset of A. But as the epsilon ball is a subset of A for all x in B, then all x in B are interior points of A, and that means that B is a subset of the interior points of A. Thank you, QED, we are done.